Okay, so so we have seen that the different equivalent resistance based on the region of operations REQ and REQP. So based on this, we'll try to draw the resistivity. So if I try to draw the resistivity, right? So we have this point where it is equal to um, BTP, and we know this point, right? Which is equal to VDD minus VTN, and then we have this point here which is equal to VDD, right? Maybe let's try to let's try to feed in this region and just try to get that this one, yeah, get this one again here. Put this here also so it becomes clear. So we have these different regions, region 1, region 2, region 3. Right? So now if I try to plot the resistance based on this region and based on the equations that we have written, so this is how my equations will look. So this is how the this is how my take different colors to plot this one. Okay, so this is basically let's try to get the different colors itself. Okay, so what if we try to draw this resistance across this V out? What we will see that this is due to the NMOS. So you know that this is in saturation region here and saturation region here. So this is how the resistance of the NMOS will be varying with V out, and this is how the resistance of the PMOS will be varying. So initially it's very high, but as it goes, as the V out increases, we'll see that it decreases, and uh, and we can see here that so it goes like this. So and this is the overall equivalent resistance between these two. So equivalent resistance. So what is observed here is that although there is a good amount of variation in the resistivity of the NMOS and the PMOS individually, but if you see the combination of the NMOS and the PMOS, the resistance is almost flat. I can say that it's not constant, it has a variation, it has like variation, some variation, but it's quite flat or it's quite smooth, So that's why the combination of the NMOS and PMOS happens to be a very good switch, because we can at least, this is because of its constant, it's good, right? If something is varying, it becomes difficult, because if we want to find out the RC time constant analysis, it becomes very difficult for NMOS and PMOS, because we cannot approximate it as RC, because this R is varying, right? You can see this R is varying with the voltage. But if we have this combination of the NMOS and PMOS, because the resistance is approximately constant, I should not say it's constant, but we can say that roughly it's constant, so it happens to be a good switch. At least we can predict the behavior, you know. So, uh, so that's why the combination of NMOS and PMOS happens to be a good switch. So I hope this point is clear. If, if you don't have any questions, I'll proceed ahead. Huh? So, any questions on this? No questions, right? Okay. So how to now let's come out. Let's so we have finally concluded that if I have these NMOS here, or I'll draw a PMOS here, something like this with bubble here up, PMOS, and the NMOS here with no bubble. So this is the notation that is generally used for transmission gate. So this is my V in, V out. This is my, maybe let this control voltage, let me call it as C, and this control voltage C bar. So if I give a voltage C here, which is actually 0 to VDD, and then this also 0 to VDD. So I need to get an opposite, right? If I want to turn it on, this will be VDD and this will be 0. If I want to turn it off, this will be 0 and this will be VDD. So this happens to be the transmission gate, and of course there will be a capacitor, parasitic capacitor CL. It's better to always mention this, that we should not forget that there is a capacitor, so it will be driving this capacitor. So the way to represent it, you know, how this it's a representation, right? Or the symbol, the way to use, because it's little difficult to, this figure is not very comfortable to draw whenever we are drawing circuits. So this is represented by a symbol. So, and the symbol is given by like this. Basically we draw through triangles, something like this. So this bubble is drawn here, bubble, right? So we have this, we have here C bar, and we have C, and this is my V in, and this is my V out. Of course, CL can be represented something like so. This is the representation of a CMOS transmission gate, like that. So now, because as we have seen that the resistivity of the combination of the PMOS and NMOS is quite constant, or I should not say it's quite relatively constant, or you can say that R total, which is given by R eq and parallel R eqp, right? So this can be represented by a if we want to represent this, it can be represented by a simplified diagram. see control here, and this is the R total. So you see, like in this case, we can easily do a simple even RC kind of approximation. RC, just like we do the RC circuit charging and discharging. So because this R total is approximately constant, we can do this kind of analysis for the for the first transistor. Yeah. Hello. 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 Hello.
Yes, sir.
Am I audible now? Hello.
Yes, sir. Now you're a little bit clear.
Clear, right? I think I don't know what happened. The network is down. So my screen is visible now. Hello.
Yes,
Hello?
sir.
Okay. Okay.
Yes,
So
sir.
okay. So now this CMOS transistor can be used to we'll see applications. Where are these applications? This is very widely used, because of this property. This is quite widely used.
Sir, the Teams is still on your slides are not visible. Still, Teams is being shown. Like your Teams screen is being shown, but not the slides.
Okay.
Can you switch to slides?
Now visible? Hello? Is it
No,
visible
sir.
now? Hello?
Yes, sir. Yes, sir. It is visible.
Okay, okay, great. Great. So, so this is quite widely used. So now we'll see some of the application, right? So suppose if I want to implement a simple AND, right? AND function, right? So which is nothing but f equal to a dot b. So if I want to implement this, then I can just simply make this use this pass transistor, right? Let's copy this one. So this will be my input A, and if I provide a B here, right? B here, I can provide this B here, but of course I need to put the inverted version of B here, right? So I'll not be drawing the capacitor here. So this will be my F, right? So it's very easy to do the N function, right? Because if I want to get this high, right, VDD, so this should also be VDD and this should also be VDD, because then if this is VDD, then this PMOS will be on, and if this is VDD, of course I need to apply the negative, right? B bar will come here, We know that control and control bar. So that's how we can get the AND function, right? So if this is off, right, this is off, definitely this, whether this is 0 or high doesn't matter, this will always be 0. And if this is, even though this is high, but if this is 0, then this also will be 0. So that's why you see that this is a simple AND function. So the other widely used case where the pass transistor or this CMOS transmission gate is used is implementation of a mux, right? So we can apply a mux or implement a mux with this one. So again, we have we can take this one here, and basically we need to take two of them. I think we don't have space here. So if I want to apply a implement a simple mux here, so again get this two of here, right? So what I need to do is I just need to connect these two nodes, right? Connect these two nodes. This is my f. Of course, for a function f, mux is used as f equal to a s bar or b dot s. So if my s is high, then b gets selected. Because if s is 1, you see this becomes 0, so, and this is 1, so the function will be only b, f equal to b. And if my s is 0, this will become 0 and s bar will be 1, so f equal to a. So that's how this is marked like that. So to do that, you can just use this a and b, right? So, and how do we select this? Because this a will be selected, right? We know that to make this AND function, so this will be s and s bar, right? So if I make s and s bar, then definitely I'll be able to get this b dot s, right? So then and definitely I then if I want to get this s bar, a dot s bar, then this will be s bar here, so that a dot s bar uh, will be this function will be implemented. And if I just combine them parallelly together, it is an OR. So either this part is selected or this part is selected, right? So that's why this is an OR function. So then if I have given an s bar here, so definitely the opposite should be given here, so s. So if I just write this s also, then it will go directly something like, um, we need an inverter here, right, to put the s bar. So definitely I'll get this s bar here, right? So then just do the connection. Wherever I have s, I can just connect this like that. I can connect this s here. So this goes at the top. Because this s bar and s bar, this can be connected, right? And then this s bar can be directly. Okay, so this is how a mux is implemented using the transmission gate. Is it clear? Hello? Is this clear? Any questions?
Yes, sir.
Okay.
Yes.
How many of you had done this one in previous courses? Some of you have done this kind of stuff in previous courses. Yes. Yes or no?
Yes, sir.
Who is speaking? Yeah.
Madhav.
Mother. Okay. Okay. So,
Yes, sir.
so it was covered, right? Okay.
Yes, sir.
Okay. Great. Then I'll not cover much. I think I'm covering it because it may not be covered for some people. So
So there are some other branch people also like who didn't have
that,
this. So it's better if you explain it to them, because
yeah.
as though it is for the majority of people, it's better that they also get a hold of it.
True,
Right?
true.
Instead
Agreed.
of
So,
leaving.
but now this is clear, right? It's quite straightforward. My explanation is clear, at least for this marks, right? So,
Yes, sir.
okay. Then I'll just show one more function. It's very easy, basically. So what I will do is I'll also give an assignment on this, so that things becomes more clear. Because if I just start writing and all, then keep writing, then things will not be clear. So that's why I'll give an assignment. So let's try to solve one more right now. So f equal to, a dot b plus a bar c bar, right, or a c. So if I want to do this, okay, we have three this term, right? So three this term. So again, let's bring my transmission gate, right? So bring my transmission gate. Let's reduce the size a little bit, right? So basically, what we have here is we have these three functions. So this is also very straightforward, right? So this is basically the this is I can say that this is basically an we can say that these two are this an OR function. So we have these two OR. Here I have this one and this one. So this point is implemented. So these are the 2 points where this OR is implemented, right? So like this a a bar c bar is implemented by this. So we can see here that this at this node this is a bar and c bar, right? So here we have this VDD and B. So here this at this node we have uh, B dot VDD, which is nothing but this B here at this node. And here we have, because this and this will be AND, so we have B bar dot C, right? So now these two will be in or like that. So at this point, at this node, it will be B or B or B bar dot C, right? B or B bar dot C, and it has to be multiplied with A. So if I multiply it A with B, of course, uh, yeah. So if we multiply with A, so it will be something like this. So multiply with A in both here and here. So it is B bar C. So, and of course here definitely I'll get this F, which is nothing but this, or AB, or A bar A B bar C. So this is how this whole logics can be implemented using transmission gate. Of course, this is one way of implementing this function, but you can use different ways, right? You can use different way to implement this, you know, this one like that. Clear? Yeah. So what I will do is I will try to give assignment. You can try solving these problems, simple problems. So then I think concepts will be easy. So if you have not already covered in the previous class, that's fine, perfectly okay. So if we just try to solve the basic assignments, uh, I think this point will be very clear like that. So now the next use of the pass transistor is designing different. Till now we have discussed about the combinational logics, right? Combinational logics. So now we'll see how this pass transistor happens to be a very good, very useful in designing sequential circuit. So you must know that you must be knowing what is this combinational and the sequential, right? So combinational is basically when this is a combination example of a combinational logic where my output is dependent on the input, right, on the present input. So if my input changes, the output will be changed. But in sequential logic, like we have this D flip-flop latch, where the output is not necessary that it will be dependent on the present input. Like it can also depend on the past input, right? It is not necessary like that. So the sequential circuits have the ability to store the past value. So that's the difference between combinational and sequential logic, right? So sequential logic is very much important whenever we are doing any digital system, because we have to remember the previous input sometime to do some calculations and to do some, like whenever we are doing some DSP, right? We have to know the past inputs. Otherwise, like if we are doing, convolution, right? Simple convolution, we should know what is the past, like that. So so depending on that, like we have to have some. We should know the sequential like that. So this past transistor happens to be a very good one of the very good. It happens to be very good, very useful for designing sequential logics. So so I just show how to implement D flip flop and D LADs like that. So using the pass transistor. So any questions here till here? Any questions? Anybody has any questions? Is it clear?
No doubt, sir. It's clear.
Okay. Okay, so let's let's implement a simple simple latch, D latch, right? So can someone tell what is the difference between D flip flop and latch? Can someone tell?
Uh, yeah, D flip flop will have a master and slave latch, right?
Okay.
Latch will.
Okay. No, what's okay? That's master and slave. That's implementation part, right?
Edge triggered and level triggered. So.
Okay, which is edge triggered and which is level triggered?
Latch is level triggered. Flip flop is edge triggered.
Okay. Okay. Good. Thank you for yeah. So latch is level triggered, right? Latch is a level triggered. So it's represented by the difference between the latch. Yeah. So we have this this is represented by this one, right? Clock, and we have this D, right? And we have this Q, right? I'm not going into the details. This is very common. So it's undergraduate stuff. So so let's if we have this kind of let's, then suppose if this is my input in the D, right? This is my input. uh, D, then this is, and if this is my clock, right? Then definitely output will be like whenever this is high, it goes something like that. In other times it is flat, right? Because it will just pass whatever is here, and or let's make it a little complicated. Fine, this is fine, I think. Yeah. So how do we implement these TLEDs? So the simple way to implement is uh, this one. So basically what it does is whenever the clock is high, the D will be equal to Q, and whenever the clock is low, so it will be just holding the past value, like what was the last value that was there, it will be just holding it, like holding it like that. So that's the how the D flip flop as the latch works. So this is how this is how the D latch, this is the simple diagram of the D latch with based on the inverters. So basically I have these two inverters. These two inverters are here. So what happens is to whenever this clock is whenever in this state or whenever it is high state, so this will be open, this will be open, sorry, this will be closed, and this will be open. So what happens, whatever the value that I gave here D, it will be, of course, D bar will come here, right? D bar, because of the inverter, this is an inverter, and finally I'll get the D. So Q will be equal to D, right? Whenever this is closed, and then of course at this time this should be open. But whenever the clock is whenever the clock is low, right, I'm supposed to hold the previous value. Then what happens is this get closed and this open, this gets open. Then what happened, like whatever the value that I had here, it just gets it is connected in a feedback cross couple path, right? So then this value gets hold, the value gets hold like that. So because these two inverters, like now if I have this high here, so let's, I think maybe let's come to the you know let's come let's try to draw these two situation, right? These two will be in opposite this one. So let me draw it properly. This is my Q. So whenever this is the situation when clock is equal to 1, right, then this is closed, right, this switch is closed, and this is open, right, this is open, it's open, this is closed, right? So this is the situation when the clock is equal to 1. So whatever the Q equal to D in this case, right, Q equal to D in this case. Now whenever the clock is 0, so whenever the clock is low or 0, this gets closed, right? This gets closed and this gets open. So what happens if this value is, if this value is suppose some Vx, so here this node will be Vx bar, right, opposite Vx bar, and so am I audible? My screen is visible, right? Hello, hello.
Yes, sir.
Okay, I don't know what some connection issues are coming again and again. So, so in this situation, whenever this is open, so if Vx was the value just before the opening, so then this will be this node will be at Vx and this will be at Vx bar, and then it will be again inverted, so it is in this node will be in Vx, right? So because this Vx, so again it goes here Vx, so this get latch, this gets latch, so that's why this value will be stored, right? This Vx value will be stored and q will be equal to Vx. So Vx was the value which was the last value of the D just before the opening, just before the opening of the switch. This Vx was D was equal to Vx. So then here I have this Vx bar Vx, so this gets, this gets latched because this value Vx value gets, uh, uh, comes as a feedback, and it gets latched, and that's why this is how this is stored like that. So this is how the delatch operation happens like that. So the implementation of these DLADs again like that. So is by using pass transistor is, so I can implement these switches, right? These switches are required here. These switches are required here. So pass transistor is used to implement this switch. So what I will have is I'll have a pass transistor here as a switch, and again a pass transistor here, the switch, these two switch. But of course this switch will be operating in an opposite way. Whenever this is high, this will be low, and whenever this is low, this will be high. So then I have my inverters here, right? This is my inverters here. Right? So I want this to be open, so I want it to be closed whenever the clock is 1. So definitely this node will be connected to clock, right? So when my clock is 1, clock is high, this will be on, and this should be open, right? So that means I should implement clock bar here, right? So if I should, this is my clock, and the clock bar will be going here, right? So clock bar, right, as I mentioned. So whenever this is high, this should be closed and this should be open. So similarly, so what I will have here is I'll have here clock. So this is clock bar basically. So clock will be here, and again the clock bar will be coming here. Like if I'm applying clock here, the clock bar will come here, and if I apply the clock bar here, clock will come here. Of course, we can do the connections, but so just to make so that the connections doesn't become clumsy. So I'm not doing the connection. We can connect this node with this and this with this one, but I don't want to make the diagram clumsy very. So this is okay. Even in exam also, even if you don't do the routing, I will understand that okay, these are connected like that. Okay. So of course, I'm not drawing the CMOS circuit. Like these are also implemented definitely with CMOS. So I'm just showing that the symbol version of the inverter, right? Right. So definitely this is uh, right. Okay. So any questions on this? No questions? Okay, great. No questions. Then I just continue to D flip flop. I'm going a little fast because I know like these things are you are very aware of the latch and flip flop. So here we are just focusing more on how it's getting implemented with the transmission gate. So that's why like that. So D flip flop, the symbol representation is something like this, right? We have an arrow here, right? This kind of this is there, so which means that this is a clock triggered. So difference between the D flip flop and the latch is a level triggered. So and whereas the D flip flop is is an edge triggered, right? So the change that D becomes equal to Q only whenever there is a transition, right? So suppose if I have some waveform here, let's draw some waveform something like this. Suppose this is my D, right? This is my D, and suppose this is my clock. So we know that only at this point the D will become equal to this Q will become equal to D, and the Q will hold the value, right? So only at the triggering point, only at the transition point. So this is a positive edge triggered because we can also have a negative edge triggered. So whenever at this transition, this whatever the value of D will get stored to Q, and it will hold till this point, till the next my transition, like that. So if you see, so the Q, how it will become is, so let's assume that it was low initially, the Q is initially. So at this point, if you see here that the D is high, so I'll have this value high, and it will be holding it like till next point, right? Till next point. So again, it will see at this point what is the value of D. So in this case, the D is high, so it will again hold till next point. So at this point, it is low, so then it will come down, right? So there's a difference between the difference between the D flip flop and D latch. So then, how do we implement a D flip flop? So basically, two latches can be combined, two D latch can be combined together to make a D flip flop, right? So uh, so if I combine, right, if I combine two DLADs, right, so this is how a D flip-flop can be implemented. If I combine these two DLADs, we'll see how this happens. Right, so combine it. So this is my D and Q of these LEDs. This is my clock terminal, P and Q. So finally this is the D and this is the Q of the entire flip-flop. So what I need to do is I just need to put an inverter and put a clock here and CLK. So this whole happens to be the D flip-flop circuit like that. So this whole happens to be the big D flip-flop. So let's try to understand the working principle like that. So working principle based on this diagram only. So let me copy it. It just stops. So how this is working as D flip-flop, how these two LEDs is working as D flip-flop, right? So imagine, you can see here that so this first LEDs will be passing, or this is basically called this master slave combination. Also, this D LEDs is also called as master, the master, and this is slave. They are also called the master slave, right? So these DLADs will be passing, right? Passing this value D equal to Q whenever the clock is high, right? Clock is high, and because I'm giving an inverted clock, so whenever this clock is low, this will be passing like that. This node will be equal to this node whenever this clock is low. Basically, this clock is low, or this will be high when this is low, right? Because of this inversion. And whereas when this clock is low, this will be holding the value, right? So holding the value of this the last value of the, as we have discussed how the DLADs work. And similarly the opposite happens for the slave like that. So what happens is whenever this just go high, right, whenever it's going high, so at this point it will be just holding the previous holding the value just at this point when the this D was equal to this, when at this point like that, at this point, so it will just identify the value, like it will be just holding this one, holding this point whenever this is uh, sorry whenever this is going high, right, whenever this is going high, sorry, this will be holding, right, this will be holding because this is inverted. So sorry, this I have drawn the diagram of negative edge trigger. So um, yeah, I just this is sorry I take it back. So this is basically, you know uh, so clock will be coming here and clock bar will be going here, right there. So this is clock, this is clock, right, and my, if I draw my clock bar, So what happens is when this clock high gets high, right? So basically this will be low. So we know that low will be holding this value, right? So low will be holding this value. So this will just hold the value at this point at the triggering point, right? So this will be holding this value, right? This will be holding this value, and then it will be directly passing to Q, right? So this will be in pass state, and this will be just in holding state. So this is just hold the value whenever this triggering happened, right? So and it will be just holding in value, and from here to here this will be just passing like that. So now when this clock becomes low again, right, this will be holding that value, the slave will be holding this value, and of course this will be in passing state. But even though it is in passing state, right, transmission state, this will not be affected because this at this point the slave will be holding. So the point here is whenever this clock in this clock goes high, the master will be holding the value of this point, right? And when the clock lows, the slave will be holding the value. So basically the master is transferring the value from this node to here, and then the slave will be transferring the value from this node to here. So in this high state, the value at this node it will be held by the master from here to here whenever this level is high, and whenever the level is low, the slave will be holding the slide, holding the value like that. So of course till the next point again at this edge, again the same thing will happen till this point like that. Is the point clear? Hello, is this point clear or not?
Yes, sir.
Okay, so I think it's already 1:10. I'll continue our discussion from this point, and of course, this is a very simple implementation because I just need to connect these two D latches together. So implementation is nothing but just I need to cascade these two, this one like that, cascade these two parts. So because now time is 1:10, so we'll continue our discussion on the next class like that. Okay, thank you. So, thank you everyone. Yeah.